Hello, everyone. Today, I would like to talk about my work on cryptography from Sublinear-Time Avg-Case hardness of time-bounded Kolmogorov complexity. And this is a joint work with Professor Rafael Past at Cornell Tech. So let me start by summarizing the history of cryptography in the last 2,000 years. And in the beginning, some artists invent some encryption scheme, and then known attacks fail on this scheme. So this scheme will be deployed primarily for military use. And finally, this scheme will be broken by someone, and we are waiting for the next new scheme. So it seems that we have been going around in this cycle for a really long time, and there's no scheme that is proved to be secure. In 1976, Diffie and Hellman proposed the genius notion of one-way functions, which gives us a way jump off of the cycle and brings us into the age of enlightenment. So a function f is one way if it is easy to compute, but it is hard to invert. So it should be able to be computed in polynomial time, and no PPT machine can invert it. So it's easy to go from the input x to the f of x, but it's hard to go from the output f of x back to the input x. And a famous example of one-way function is to use the input x to pick two large primes p and q, and we output p times q. So people don't know how to factor p times q, and this function is assumed to be one way. And let's look at the formal definition. So first, we sample a string x among a random n-bit strings, and we compute y equals f of x. And for any PPT machine A, the probability that A on input Y finds a pre-image of Y is at most a negligible amount. And the good news is that one-way functions are known to be both necessary and sufficient for a bunch of private key crypto primitives, such as private key encryption, pseudorandom generators, digital signatures, and so on. Although PKE, MTC, and obfuscation are not included, whether one-way function exists is the most important problem in cryptography. And very recently, Liu and Past 20 shows a characterization of one-way functions. They show that for any polynomial that is at least 1.1n, one-way functions exist if and only if MKTP s equals n minus of log n is mildly hard on average. And MKTP_s denotes the set of strings x with T-time-bounded Kolmogorov complexity at most s of length of x. And then let us introduce the notion of time-bounded Kolmogorov complexity. So given a truth table x of length n of a Boolean function, we ask what is the size of the smallest program that computes x. And when the notion of program is taken to be circuits, we obtain minimal circuit size problem. And when the program is taken to be time-bounded Turing machines, we obtain T-time-bounded Kolmogorov complexity problem. And there are many ways to define time-bounded Kolmogorov complexity. We here only consider the local compression version. And for any string x, we let kt of x denotes the length of the shortest program pi, such that pi computes truth table x within time t of length of x. And more formally, we fix a universal Turing machine U and a running time bound t. We are looking for the length of the shortest program pi, such that for all coordinates I in x, the program pi on input I will output the ith bit of x within time t of length of x when simulated on universal Turing machine U. So the language MKTP_s just denotes the set of truth table x that has kt complexity at most s of length of x. And recall that Liu and Past 20 show that one-way functions exist if and only if MKTP with threshold s equals n minus of log n is mildly hard on average. And we ask, what happens if the threshold n is much smaller than n. So does the average case hardness of MKTP polylog n imply one-way functions, or is MKTP polylog n any harder than MKTP n minus of log n in average case? And our main theorem demonstrates that for an appropriate notion of mild average case hardness, the existence of sub-exponential secure one-way function is equivalent to mild average case hardness of MKTP polylog n with respect to just sublinear average case algorithms. And the existence of quasi-polynomially secure one-way function is equivalent to mild average case hardness of MKTP 2 to the power of all square root log n with respect to sublinear algorithms. So we have two surprising phenomena here. First, proving the existence of sub-exponential one-way functions is equivalent to proving a sublinear average case lower bound. And second, the threshold S for the MKTP-S problem captures the quantitative hardness of one-way functions, and the smaller S is, the harder the one-way functions we obtain. In addition, we show some unconditional lower bounds that come surprisingly close to unconditionally deducing the existence of one-way functions. First, we show that MKTP polylog n is worst case hard for sublinear time algorithms. And this lower bound doesn't prove an average case result. And second, we show that MKTP n minus log n is mildly average case hard for algorithms in d time t over n cubed. And this lower bound doesn't prove a result for small threshold. So it only works when S equals n minus of log n. And let us introduce the notion of average case hardness for sparse languages that we rely on. The observation here is that the MKTP S is actually very sparse. And consider any string x in MKTP S. We know that kt of x is at most s of n. So there must exist a Turing machine of size at most s of n that produce the truth table x. However, there are at most 2 to the power of s of n such machines, and we conclude that the number of yes instances in MKTP-S is at most 2 to the power of s of n. And the issue with this is that when s equals n over 2, the trivial output in no heuristic succeeds with very, very high probability, namely 1 minus 1 over 2 to the power of n over 2. So MKTP-S is trivially easy on average. So luckily, the notion of an errorless heuristic makes sense for MKTP-S. And we say that H is an errorless heuristic for L if H outputs spot with probability at most mu, and if H of x doesn't output, it is guaranteed that H of x outputs the correct answer, namely L of x. And we can see that MKTP-S doesn't have a trivial errorless heuristic, since the trivial outputting no heuristic will make mistakes on yes instance, but an errorless heuristic will never make a mistake. And we are ready to present our notion of average case hardness for sparse languages. We say that H is a heuristic star for the language L if H succeeds with high probability on yes instances, and H also succeeds with high probability on no instances. And we say that MKTP-S is mildly hard on average star if there exists a polynomial P such that MKTP-S does not have 1 over P heuristic star with respect to infinitely many input length. And let us look into our main theorem in more detail. So let F be a nice class of super polynomial functions. And by nice class, we mean all classes such as all functions in F this function is strictly increasing, and the class F is closed under polynomial composition. So basically, all a class of functions we can imagine are nice, except for the exponential family. So the class of next exponential functions is not closed under polynomial composition, so it is not nice. And so we let F be a nice class of superpolynomial functions, and let T be a polynomial larger than 1.1n. And we show that the following are equivalent. First, T hard non-uniform secure one-way function exists. And second, MKTP inverse T plus O of 1 is mildly hard on average star with respect to sublinear algorithms. And third, MKTP n over O of 1 is mildly hard on average star with respect to T time non-uniform algorithms. And we have the following two corollaries. First, quasi-polynomial secure one-way function exists if and only if MKTP 2 to the power of O of square root log n is sublinear mildly hard on average star. And second, sub-exponential secure one-way function exists if and only if MKTP polylog n is sublinear mildly hard on average star. Let us mention some related work. And there is very recently there is a line of work focusing on hardness magnification, in which they show that very weak lower bounds imply breakthrough separations in complexity theory. And they do it by compressing an instance in a sparse language into another instance that is much shorter. And our results show a hardness magnification for one-way functions. And there are also some works focusing on fine-grained complexity, where they show that fine-grained lower bounds imply the existence of fine-grained one-way functions, so that are secure with respect to a priori bounded polynomial time attacker. And our results show that sublinear lower bounds is equivalent to super polynomial hard one-way functions. Okay, so let's look at our proof in more detail. And the proof goes from the second to the third and to the first, and then to the second. So we'll obtain an equivalence. So let us look into the proof for theorem 1. And theorem 1 basically says that assume there exists a function S in the inverse family F, such that MKTPS is mildly hard on average star with respect to sublinear time algorithms. Then for any constant gamma, there exists a function T in F, such that MKTP n over gamma is mildly hard on average star with respect to T time non-uniform algorithm. And we can see it is a hardness magnification result. Just take F to be the family of sub-exponential functions and take S to be polylog n. We obtain that if MKTPS is mildly hard on average star with respect to sublinear attacker, then MKTP n over gamma is mildly hard on average star with respect to sub-exponential attackers. And we prove theorem 1 by assuming for contradiction that there exists a sub-exponential time heuristic star H prime for MKTP n over gamma, and we will construct a sublinear time algorithm heuristic star H for MKTPS. So let's look at the reduction. Given an instance x of length n, our goal is to decide whether kt of x is at most s of n. So you can see here x is an n-bit string, and what did we do? We first truncate x to its first gamma times s of n bits, and we will obtain the new string x prime. So h of x simply feeds x prime to h prime and outputs h prime of x prime, where h prime is the sub-exponential time heuristic for MKTP n over gamma. So although here h prime runs in sub-exponential time, this x prime is so short such that H, the heuristic, just runs in sublinear time in length of x. Since here Sn is just polylog n, so x prime is a string of polylog n bits. So although H prime runs in sub-exponential time, but it runs on a string of length polylog n, so overall its running time is just sublinear. And somewhat surprisingly, this simple reduction works. And here are some of key insights. First, on random yes instances, they won't be projected down to random yes instances, since the static distance is far, but the relative distance actually isn't far. So we can show that on random yes instances, our heuristic is a good heuristic star. And on random no instances, they are close to random. So when they get projected down to a length string of length gamma times s of n bits, they still close to random. And thus we show that H is also a heuristic star conditioned on no instances, which concludes the proof. And we refer to the full paper for more details in the proof. So we conclude the proof of theorem 1, and let's look at the proof for theorem 2, which basically says that assume MKTP n over gamma is mildly Hardon average star with respect to sub-exponential time algorithms, and then sub-exponential wave functions exist. And the proof of theorem 2 closely follows from the results in Liu and past 20, and we here skip the proof. And let's look at theorem 3. So theorem 3 says that assume a sub-exponential hard one-way function exists, then MKTPS is mildly Hardon average star. So to prove theorem 3, it is helpful to introduce the following object. We say a function g that maps n bits to n plus n to the epsilon bits is a conditionally secure entropy-preserving PRG with sublinear strength if g satisfies pseudo-randomness property and entropy-preserving property. So first, g on input un conditioned on some event e is computationally indistinguishable from uniform distribution over n plus n to the epsilon bits strings. And then g on input un conditioned on the event e has Shannon entropy at least n minus of log n. And in the paper, we show that the existence of count EP PRG with sublinear strength implies that MKTPS is mildly Hardon average star. So it remains to construct a count EP PRG with sublinear strength. And in Liu and past 20, they show that the existence of one-way functions imply the existence of count EP PRG with logarithmic strength. So here to construct a PRG with sublinear strength, why not we do repeated applications of PRGs? That is, we do g of g of g of g to construct a PRG with large strength from a PRG with low strength. And unfortunately, this doesn't give us a count EP PRG with sublinear strength, since count EP PRG is only conditionally secure, and it is a PRG conditioned on some events E. And the probability that in each application, this event holds is very tiny, and thus this construction doesn't work. And we here give a new construction of a count EP PRG, which gives sublinear strength. So let's look at our construction. We start with one-way function. The existence of one-way function imply the existence of PRG by here 99. And then we let G to be a length doubling PRG. So the first step is to sample I as a guess of the degeneracy of GX. And the degeneracy of Gx guarantees that if I is the correct degeneracy, then given G of x, the random variable x has mean entropy at least I. So if x has mean entropy at least I, we can apply hash functions as extractors. So our construction G star takes I, x, h1 as inputs, and it outputs h1, g of x, and h1 applied on the input x. So here, the output of hash function h1 is I minus of log n bits, where I is randomly chosen in the input. However, this is not pseudo-random because the information about I is leaking by the length of h1 of x, and our solution is to apply another hash function on the whole output. So we obtain G prime that's on inputs I, x, h1, h2, outputs h1, h2, h2 of x, G of x of h1 of x. And we only need to show that G prime is a good entropy preserving PRG conditioned on the event that I is a good gas. So we can say that when I is a good gas, G of x and h1 of x has entropy roughly n minus of log n bits. And it remains to show that G prime is pseudo-random. So to show that G prime is pseudo-random, we actually need a security reduction. So we need to show that if there exists a distinguisher D prime that breaks G prime conditioned on that I is a good correct gas, then there exists a distinguisher D that breaks the original PRG G. And the bad news here is that our distinguisher D does not know which I is the correct I. And guessing a random I doesn't work, as the distinguisher D prime can be very bad when the guess is incorrect. And of course, we don't know how to compute I efficiently either. And our central technical contribution is to deal with this issue. And we refer to our paper for more details in the proof. And by now, we have seen the proof for theorem 3, and combining theorem 1, 2, 3 together, we obtain an equivalence. In conclusion, we show that deducing the existence of sub-exponential one-way functions is equivalent to proving an Avg-Case lower bound with respect to sublinear attackers. And then the threshold S for the MTTPS captures the quantitative hardness of one-way functions. And our main technical contribution is the notion of an entropy preserving PRG with large strength. And we show that the existence of such PRG is implied by the existence of one-way functions. And we left it as an open problem to characterize exponential hard one-way functions by Avg-Case hardness of a natural problem. And the caveat here is that Yale's hardness amplification lemma for one-way functions does not work. It only can prove that we can obtain sub-exponential secure one-way function from weak one-way functions. And thank you for listening.